The Moon is 384,400 kilometers from Earth. The fastest way there? Elon Musk thinks he's found it. In this countdown, we'll break down the 3 biggest changes in SpaceX's new lunar plan, from advanced onboard refueling to unprecedented flight path precision. We'll finish with the one challenge still standing between us and the first non-stop lunar flight in human history. Imagine leaving Earth and flying straight toward the Moon without stopping anywhere along the way. No looping around Earth to build speed, no waiting for complex orbital alignments, and no detours to a space station for a quick refuel. Just one continuous burn that takes you from the launch pad to lunar orbit in a single, streamlined trip. That's the idea Elon Musk wants to make possible with Starship, and it's a bold break from how we've always done lunar missions. If you look at how most moon missions work today, you'll see why this kind of direct shot has never been standard practice. Even the Apollo missions didn't simply head there in a straight line. After launch, the spacecraft usually reaches Earth orbit, coasts for a while, then performs a major burn to push out toward the Moon. Along the way, smaller course adjustments keep it on target. Multi-stage rockets mean that large fuel tanks are dropped as they empty, and long coasting periods are used to save propellant. The whole process is carefully timed, and every maneuver is tuned to get the most from limited fuel reserves. That approach works, but it's not fast, and it allows little flexibility if plans need to change mid-flight. The biggest obstacle to skipping all that is simply fuel. A rocket carrying enough liquid methane and oxygen for a direct route would be so heavy that it couldn't lift off efficiently or carry useful payloads. Even with a huge booster like SpaceX's Super Heavy, filling Starship with enough propellant to complete a high-speed lunar transit without stopping would leave almost no room for cargo or crew accommodations. This is where Musk's new plan changes the equation. Instead of overloading the craft at launch, Starship could go up partly fueled and then meet a dedicated Starship tanker variant already in orbit. The tanker delivers a fresh load of propellant in microgravity before heading back to Earth. With its tanks topped up in space, the lunar Starship could then fire its engines for as long as needed to take the shortest possible route toward the Moon. It's basically the rocket version of topping up a jet in mid-air instead of landing at an airport, and it removes one of the most stubborn design limits of interplanetary flights. Aerospace engineers point out that pulling this off is far from routine. The 2 massive ships would have to dock with high precision, line up connection ports in the vacuum of space, and transfer cryogenic fuel without excessive boil-off. Even small losses in the process could cut into the performance needed for a direct lunar run. But SpaceX has already been experimenting with in-orbit propellant transfers in smaller test scenarios to learn what works and what needs to improve. One major milestone came when they performed a simulated fuel transfer sequence with 2 docked spacecraft. While it didn't move actual fuel in the quantities a real mission would need, it proved that Starship's ports and locking systems could hold stable through the maneuvers. Engineers also gathered data on how liquid methane settles in orbit, which is key to pumping it between tanks in weightlessness. Now that the ability to refuel mid-flight is closer to reality, the old limits on how far Starship can travel in one continuous journey are starting to fall away. We're no longer talking about whether the rocket can physically make the trip. It's about how accurately it can aim and stay on target for hundreds of thousands of kilometers. And that leads to the next challenge: hitting the Moon with pinpoint precision. Even a 1-degree error in your course might not sound like much, but when you're shooting for the Moon, that small slip can push you thousands of kilometers off target. And unlike an Earth orbit mission, there's no easy second chance to just swing back around. If you miss, you're completely off the intended trajectory, and the mission risks failing before it ever reaches lunar orbit. Traditional lunar missions avoid that by building in wide safety margins. Instead of heading straight at the Moon, they take more measured routes with extra time baked in for corrections. A spacecraft might follow a longer, looping path that lets mission control monitor its position for days before a big approach burn. That approach buys predictability, but it also stretches the trip into a slower, less fuel-efficient process. Direct flights cut out almost all of that slack. There's no long orbital coast to refine your path, and the window for correction shrinks from days to hours. The calculations have to be incredibly tight from the moment engines ignite, because even slight deviations add up fast over the nearly 400,000 kilometers to the moon. For a crewed mission, that's not just a math challenge. It's a safety issue that has to be solved before such flights become routine. To tackle this, Musk is pushing for new navigation and propulsion control systems on Starship. These go beyond the kinds of autopilot systems used for current launches. The idea is to combine extremely responsive thrusters with constant real-time guidance from onboard AI. Instead of depending only on ground-based tracking and pre-planned burns, the spacecraft could make small, rapid-fire adjustments on its own while speeding through deep space. This turns navigation into something closer to active piloting rather than passive cruising. It's a bit like trying to thread a needle that's not only moving, but also changing direction slightly as you approach. Except that needle is hundreds of thousands of kilometers away, and every move you make is delayed by the time it takes instructions to travel back and forth. The solution is autonomous predictive control. The ship predicts its own drift minutes or even hours ahead, then corrects before those errors grow too large. Mission planning teams work on software that models these trajectories far in advance, but what's changing now is the level of precision and speed those models can achieve. Enhanced simulation tools factor in the constantly shifting position of the moon, gravitational influences from other bodies, and even the tiny thrust from venting warm gases. All of that gets crunched into flight plans that update in real time, guiding Starship to make efficient course adjustments without overshooting or wasting fuel. Early simulations and test flights in near-Earth space suggest these systems could shave significant time off a lunar trip. By keeping the path tightly locked, Starship might cut days from the journey, arriving faster and with enough orbital energy to enter lunar orbit directly instead of spending extra loops slowing down. That's not just a speed boost. It changes how missions are scheduled, making launches less dependent on narrow timing windows. So, while mid-space refueling might make the direct route possible at all, navigation technology will determine whether that trip can actually succeed. The margin for error is so small that every sensor, thruster, and algorithm on board needs to work in perfect sync. And with those two pieces of the puzzle lining up, there's only one unpredictable hurdle left before direct flights to the moon move from experiments to reality. The big leap left for direct moon flights isn't about fuel or navigation anymore. It's about making sure launches at this scale are reliable and safe every single time. Starship has to handle the immense stress of liftoff, survive the climb, and operate without critical failures all the way to lunar orbit. If you want to see how close we're getting, keep an eye on the next round of Starship test flights. Each launch moves the goalposts forward. The moment a direct moon flight becomes as routine as crossing the Atlantic, the path to the rest of the solar system opens wide.